We're going to start with an introduction to the material we're going to be covering in the linear algebra section. And I want to do this for two reasons. First, I'd like you to know the topics that we're going to cover because we are going to do a lot of applications. Some of them will be relevant to machine learning. Secondly, though, I want you to kind of see the structure that we're going to use because it's going to be very similar to what we do when we cover the section on probability next. We're going to start off talking about some of the basics, and these are basically facts and things that you probably already know. It'll be a brief review, refresher. We're going to look at them in maybe a little more theoretical detail than you did, however. And of course, the first thing we always start off with is we start off with the solution to the linear system AX is equal to B. And unlike what you might have done at the undergraduate level where you only looked at Gaussian elimination, we're going to actually consider two other methods, LU decomposition, which is how most people actually solve linear systems numerically, and finally QR decomposition, which is a technique that is reserved for special types of systems, but they're very common when we do statistics, for example. We want to look at the properties of these solutions. It turns out that there is some really rich theory underlying this, and we're going to look at four basic properties of the solutions of a linear system of equations. Next, we're going to look at some operations we can do with matrices. So we pretty much covered the solutions for linear systems. Now we want to focus on matrices, and we're going to talk about properties of the transpose, the inverse, and the determinant. We're going to go into the transpose and inverse in great detail. The determinant is theoretically a little more challenging, and it would take us a little far afield to really be able to cover that completely. So we're simply going to hit the highlights, talk about the important properties of determinants. And last, we're going to briefly touch on eigenvectors and eigenvalues. We're going to talk about what they are, especially how they're computed. So for large matrices, a lot of people don't know how to compute eigenvectors and eigenvalues. We're going to talk about some applications that we use a great deal. And if we have time, we'll talk a little bit about generalized eigenvalues and where they come in. And that'll wrap up week one. Then week two, we're going to go on to more advanced topics. So we're going to start off looking at linear equations in a more abstract way. We're going to start thinking of matrices as transformations and vectors as elements they operate on in an abstract space called a vector space. And we're going to talk about many important terms and concepts associated with vector spaces. We're going to prove some important theorems about a spanning set and a basis set. And once we have this theoretical background, then we can examine vector spaces in the context of linear systems. And so specifically, we're going to look at the four fundamental subspaces of the coefficient matrix. And we're going to see that they lead to a very important result called the rank nullity theorem. And that's going to pretty much cover our in-depth analysis of linear systems. From there, we're going to go on and talk about applications. So once we understand eigenvectors and eigenvalues and bases, we can then look into how QR decompositions are done, Gram-Schmidt orthogonalization, similarity transformations, which are very important, singular value decompositions, which we use for rectangular matrices, and pseudo-inverses. Okay, and then we're going to talk about some applications, and specifically we'll talk about principal component analysis as they're applied to covariance matrices. What I want to do in the remainder of this video is just give some very general background about linear algebra. So first we have to know what it means to have a linear equation and n variables. And like most of the things that we've studied, you've noticed there's this algebra geometry duality. Okay, everything that has an algebraic representation can also be thought of as some sort of geometric object, and conversely, and linear equations are no different. So we say that any equation that has the following form, where x1 through xn are considered variables and a1 through an are typically going to be real numbers along with b, this is what we're going to call a linear equation in n variables. Now, it turns out that for any vector in Rn that satisfies a linear equation in n variables, it represents the points that lie on a plane in a Euclidean n-dimensional space. And conversely, if I know a particular plane in Rn, then I know that there is a linear equation that corresponds to it. Okay? Now, one linear equation is generally not of great interest to us. So we're going to start looking at systems of linear equations. And this is just any finite number of linear equations that are all in the same variable. So this is an example of where we have a system of n linear equations and n unknowns. Okay? And we know that we can write this in a rather compact matrix representation as AX is equal to B, where X and B are vectors with their respective dimensions. X is the solution vector that we seek. B is some vector of constants that we're given. And A is the coefficient matrix. It's an m by n matrix. And we're going to use some specialized notation. Sometimes we're going to want to talk about the ith row of A, which we're going to write as follows. This is actually similar to how you specify a row of a matrix when you're doing a computer language, right? And we're also going to talk about the jth column of A. We're going to have the following notation for it. So the last thing, oh, and I also want to mention that we're also going to use the identity matrix a great deal. And so just to be careful as to what the dimensions of it is, we're just going to write I sub n for the n by n identity matrix. Okay, and that's all for linear algebra introduction. Next, we're going to start talking about the solutions to the linear system AX is equal to B.